Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. We're doing multivariable calculus. This is chapter 2, double and triple integrals. We're going to do surface area, and this time the previous lecture was in the playlist was deriving how we get this clever formula for what surface area is. Why is it the area of that surface that you're going to have is going to be the double integral over your region D, and then all of a sudden you get the square root of fx squared plus fy squared plus 1 dA. Linear algebra is where we derive that. This time we're just going to compute a bunch of examples on how to actually compute the surface area once we have the formula. Basically what you wanted as a student. Let's do that. Example 1 is find the area of the surface z equals x plus y squared, which is lying above the triangle with vertices 0, 0, 0, 1, and 1, 0. Let's sketch that. As we're doing this, I do it in stages. Stage 1, I have to take this word problem and get the region correct. Whatever they described it, hopefully I get this triangle right. Then when I've drawn that triangle usually, then I say to myself, I have to phrase that as either type 1 region, type 2 region in Cartesian, or polar. That's what's going to happen. That's sort of stage 2. Stage 1, take the words and draw your region. Stage 2, find your bounds. Are you going to phrase it as type 1, type 2, or polar? And then once you've done that, you'll have your bounds. You phrase whatever you're computing, surface area or whatever double integral or application you're doing. You write that double integral with your bounds, and then you compute the iterated integral, whether the bounds have just constants or the functions of each other in there. So stage 1, take the horrible sentence. It says my region is a triangle. Let's draw the triangle, and then we'll phrase that triangle with bounds of type 1 region. There's my Cartesian product, or plane. It says I have the point 0, 0. The point x is 0 and y is 1. And the point 1, 1. So this is our region D. Then what I'm going to do is I'm going to phrase this as a type 1 region. This is y equals 1. This is x equals 0. This is x equals 1. So I can say that x is going to go from 0 to 1. And then I'm going to phrase this and say y is going to go from this guy, whoever that is, to y equals 1. It turns out when I look at that, that's not hard to phrase, but that's the straight line y equals x. That says 0 is less than or equal to x is less than or equal to 1, my stage 2. And then x is less than or equal to y is less than or equal to 1 are my bounds for my function. Stage 3, essentially now I have my bounds, I set that up, I have the area of the surface. The 2 stages we really should do, I guess, is from here, we should rotate that and put that into our 3-dimensional scenario now, where I have this guy, and now that's my region, where I have y, and I have x, and I have z. And then we're going to have some kind of the surface, which is our region. Again, I'm just sketching. I didn't actually sketch what that guy looks like. But that's the thing we're calculating now, is the area of the surface underneath our region, which is a triangular region. And that's going to be some number. How do we compute that? That's going to be computed as the double integral over our region D of the square root of fx squared plus fy squared plus 1 dA. What do we have to compute? Now we have to compute all those pieces, put it in there, and then compute the antiderivative. We have our bounds. Once we do that, we have to simplify. I don't like to put it all in and try to eat a steak, or you don't eat the cow. You chop it up into a piece of pieces, and then you eat a steak. And even that, I'm not stuffing the steak in my mouth. I'm cutting it into pieces. So we're going to chop this up, prep it a little bit, and then we'll devour it. I need fx is 1, luckily. Good. Fy is 2y. Therefore, the square root of fx squared plus fy squared plus 1 is equal to the square root of 1 plus 2y squared plus 1, which is equal to the square root of 2 plus 4y squared. Now what are we going to do? That goes here, and we put our bounds in. And luckily, this will help us out a little bit, but we may have to change the order of what we set up, and then we'll look at whether we picked the right thing. And this is where first time, which is good that I picked it, where we may want to interchange, and they're going to ask you on questions sometimes to redraw it and change the order of integration to make this easier. Otherwise, how do I integrate this guy? Let's set it up first. What does that give me? That says that the area of the surface for this function underneath this triangle is equal to the integral from 0 to 1, the integral from x to 1 of the square root of 2 plus 4y squared dy dx. Noticing this, well, we can keep going this way, but I would have to use trigonometric substitution from here because I have the square root of something squared plus a constant. So we can use some funny business and do a bunch of work and get us out of there. Or just like on a lot of the homework or sometimes on exam questions, they'll say resketch it and rechange the order of integration so that you can make this more computable, or sometimes it's impossible. It's a non-elementary function with one of the variables. You switch it and then it's not so bad. So here, what I notice is I stick to my guns, and you will probably too, and so I phrase it as y as functions of x, because that's the one I stick to when I'm going to normally do that. I do dy first, and I phrase it as a type 1 region if I can in the plane, or polar. Type 2 is only when I can't do that. But we're now going to rephrase it as a type 2 region, because these functions are invertible, so I can phrase it as type 1 or type 2. It's both, technically. Raising it as type 2 instead, this is type 1. As a type 2 region, if we want to phrase it that way, because this function is invertible, y equals x. There's the inverse. Just write it like this. How am I going to do that? X is y. So what that says now, I can phrase that as 0 is less than or equal to y is less than or equal to 1. And now x goes from 0 to y. What's going to happen there? Well, first of all, there's no x in there, so when I switch these, I can integrate, and then I'm only going to get an x, but then when I put that in there, I'm going to sub y for x, and then I'll have the differential. I can make a regular substitution. Let's do that using this. This is also equal to, by changing the bounds, by re-looking at this, this is also equal to the integral from 0 to 1, from 0 to x, of the square root of 2 plus 4y squared, now dx. dy. I've changed the order of integration, but it's not regular Fubini's. This is Forte Fubini's, which is what? You have to make sure you redraw it and make sure you rephrase it as a type 1 and type 2 by inverting those functions. Otherwise, you can't just switch them when they've got variables in there. What does this give me now? Now we're ready to compute. This is the integral from 0 to 1 of the square root of 2 plus 4y squared times x evaluated from, or I put the wrong guy in there because I got excited, from 0 to y. This is a constant, so I just get an x. Now dy, this is now equal to the integral from 0 to 1 of the square root of 2 plus 4y squared. I put the y where the x is. Now I can make a substitution, which won't be so bad. What am I going to do? I use w because I use u and v for integration by parts. If you have to do more than one step and you've already used u, and then you have to use integration by parts, then you're going to sub u is equal to u, and that's a tautology, but it doesn't help me very much. So w is regular substitution. W is going to be what? The hot mess underneath the function. I need to see the function and its derivative appearing for substitution. So this is going to be 2 plus 4y squared. Then, already seeing that I have y dy, I'm going to say that 1 over 8 dw is y dy. Oh, careful. Either have to temporarily, or I'm just going to do it. When y is 0, that says w is 2. And when y is 1, that says w is 6. This says that this integral is equal to the integral from 2 to 6 of w to the 1/2 1 over 8 dw, which is equal to 1 over 8 times 1 over 1/2 plus 1 w to the 1/2 plus 1, evaluated from 2 to 6, which is equal to 1 over 8. What do I get? 3 over 2, so 2 over 3 times w to the 3 over 2, evaluated from 2 to 6, which is going to be cancel, 1 over 12, 6 to the 3 over 2 minus 2 to the 3 over 2, which you can probably keep like that. Or if you really want, people like to write this 3 over 2. One of them you can take out. This is 6 root 6, and 2 to the 3 over 2 is 2 root 2, but close enough. And that's the surface area of this surface underneath the triangle D. Next question. Example 2, let's find the surface area of the part of the sphere x squared plus y squared plus z squared equals 4 lying above z equals 1. So I have the sphere which is centered at the origin of radius 2, and then I have a plane z equals 1 cutting it. And then what do we want? We want the surface area of this region. Basically, what's the surface area of your hair after your mom gives you the bowl cut? Sadness is what the surface area equals in that case. But we're going to calculate the numerical value of it given a radius of, you could change it to r instead. We're going to use 2. When we have that, notice that when does that happen? We have to find our region D, setting these up. Again, this is stage 1. Make sure you take the word problem, set up the scenario that you're doing, and find your region correctly. Why is it root 3, the region D? Not 2. R doesn't go from 0 to 2, it's root 3, because when Z is 1, we put that in here, that's where it cuts. So that says we're going to get x squared plus y squared plus 1 squared equals 4. And that's going to say x squared plus y squared equals 3. And then that is x squared plus y squared equals the square root of 3 squared. So this has center 0, 0 and radius root 3, not 2 like you might have thought from the original setup of the equation. The big sphere has radius 2, but where it cuts, it's root 3 is the radius, is what it's saying. And then that's projected down onto the plane, and then that's our planar region D. So what does that say to us? X squared plus y squared is equal to root 3, and that gives us in polar coordinates. I'm going to use the much nicer. This gives me 0 is less than or equal to r is less than or equal to root 3, and 0 is less than or equal to theta is less than or equal to 2 pi because I have 1 full revolution. Then what am I going to do with that? I have to calculate surface area. Surface area of what though? Oh, this is going to be a hot mess now. Z. And notice I'm supposed to say too, notice that Z equals 1 intersected the positive hemisphere of this guy. So I can't write this surface as a unique function of one function of 2 variables. I have to use 2. Z is the positive square root of this hot mess, and Z is the negative square root of this hot mess solving. But luckily, I'm going to get Z is equal to the square root positive because it intersected on the top half, the square root of 4 minus x squared minus y squared. This is my function of 2 variables, and that's what we're going to find. This is now the function Z equals the square root of 4 minus x squared minus y squared. Now I have a function of 2 variables, and I can express it like that. I have the bounds. What I'm going to do is write that in polar coordinates because I know that x squared plus y squared equals r squared. Therefore, that gives me the area of the surface of the part of the sphere which is above the plane z equals 1. I can now phrase as the function as a function of 2 variables. Then I'm going to turn it into polar coordinates. I found my region phrased in terms of polar coordinates. That is going to be the double integral over the region D of the square root of x squared plus fy squared plus 1 dA. Or I have to change this into polar coordinates, but we'll do this first, and we'll take them with respect to Cartesian. Then we'll turn it into polar after. What do I need? I need fx of my function of 2 variables. Oh no, what is that? Can you do it in your head? This is a fraction 1/2. I get 1/2 4 minus x squared minus y squared to the minus 1/2. And then by the chain rule, I'm going to get negative 2x. Cancel, cancel. So this is negative x over the square root of 4 minus x squared minus y squared. Similarly, I can squeeze it in there. Fy is exactly the same computation, but with respect to y, because of the symmetry here, I'm going to get this is negative y over the square root of 4 minus x squared minus y squared. Then I'm going to square those. Then I'm going to add 1. We're going to get a common denominator. Let's do that next. Using those 2 pieces of information, I have fx and fy. I have to square them and add 1 and then take the square root. Again, I like to do it in pieces, chop the onions and chop the carrots up and everything, and then we'll put it in the pot and stir. I like stirring the pot, but you got to prep it first and then I let it loose. What do we get? This was negative 4 over the square root of 4 minus x squared. That should be an x. Negative x over the square root of 4 minus x squared minus y squared plus negative y over the square root of 4 minus x squared minus y squared plus 1. I know I'll go all the way through it and then we'll erase it when I simplify. This is x squared plus y squared. These two have the common denominator, so I can combine those. I'm combining these two. X squared plus y squared over 4 minus x squared minus y squared plus 1. Now I need a common denominator. Oh, this is going to be 4 minus x squared minus y squared over 4 minus x squared minus y squared. Now I can add 3 across on the top. This is going to be 4 over 4 minus x squared minus y squared. And then we need the square root of that. This is 2 over the square root of 4 minus x squared minus y squared, and x squared plus y squared equals r squared. So we're going to get 2 over the square root of 4 minus r squared. R d theta will save us and we'll have a regular substitution. Let's do that now. Moving that up, basically now I've computed what this hot mess is and turned it into polar coordinates because I looked at my region. My region is a sphere of radius root 3. So my bounds now are 0 is less than or equal to r is less than or equal to root 3, and 0 is less than or equal to theta is less than or equal to 2 pi, 1 full revolution. And then now I can phrase this in polar coordinates. We found out this is going to be the integral from 0 to 2 pi, the integral from 0 to root 3 of what is this hot mess in terms of r. It was 2 over the square root of 4 minus r squared. And then like magic, we're going to get r dr d theta, and the 2's even there for the substitution rule. The negative's not, but close enough. Now what are we going to do with that? Now we've set it up. Now we actually do stage 3. We compute the double integral. This is equal to the integral from 0 to 2 pi d theta, I'm splitting it this time, times the integral from 0 to root 3 of 2r dr over the square root of 4 minus r squared. I'm going to let w equal 4 minus r squared. Then negative dw equals 2r dr. What am I going to do with that? Oh, and when r is 0, this says w is 4. When r is root 3, this says w is 4 minus 3, which is 1. Those are upside down, but I have a negative, and then I'm going to use the property of one-dimensional integrals to flip that. This is going to give me, this is theta from 0 to 2 pi. That antiderivative I know how to do. Antiderivative of 1 is theta. And then this one now I'm going to have, this is the integral from 4 to 1 of w to the negative 1/2 negative dw. I can invert that. That gives me 2 pi, computing this one, times w from 1 to 4 of w to the negative 1/2 dw. This is going to give me 2 pi times 2w to the 1/2 evaluated from 1 to 4, which is going to give me 2 pi times 2, and then I have 4 to the 1/2 minus 1 to the 1/2, which is 4 pi times, what do I get? Oh, I get 2 minus 1, which is 4 pi. Let's do one more. All right, I found this one in the back of an unnamed calculus book, which most universities use. You know which one I'm talking about. And it said, use a computer algebra system to find the exact area under this surface. Over, it should probably say, this rectangle. Under this guy, over this one. What we're going to do is we're not going to use a computer algebra system. We're going to use a wizard. So we're going to use wizards to do this, not computer algebra systems. After I catch the mosquito, there you are. Got him. How do we use wizards to compute this exact surface area? We use the same definition. We set it up and we get a horrible trigonometric substitution. We crush that out and we get the answer. What do we have to do to set this up as usual? First of all, the bounds are really nice. It gave me a rectangle. That rectangle is a square, in fact. That means they already gave me my bounds, which is nice. And I can even use Frobenius because it's an iterated integral with constants in the bounds. And this says that the area of the surface is going to be the double integral over my region D of the square root of fx squared plus fy squared plus 1 dA. Computing, this is going to give me fx equals 2x. So fx squared is 4x squared. Fy is 2, so fy squared is 4. Therefore, this is going to give me fx squared plus fy squared plus 1 is equal to 4x squared plus 4 plus 1, which is 5. And that says this hot mess is going to give me the area of that surface over that unit square is equal to the integral from 0 to 1, the integral from 0 to 1 of the square root of 4x squared plus 5 dy dx, which is, by the fundamental theorem of calculus, doing this once, I'm going to get y evaluated from 0 to 1, which is just 1, which gives me the integral from 0 to 1 of the square root of 4x squared plus 5 dx. This is apparently where the average person gives up and uses a computer algebra system to compute this. This is, you should be Pavlovian by now. I have x squared and then plus a constant. That's trigonometric substitution with a tan. I'm going to clean that up because the first rule is x shouldn't have anything in the front. I'm going to pull out a 4 out of both terms. There isn't a 4 in this term. Yeah, there is, 4 over 4. And we're going to take it out. Let's do that and move it up. We realize that we can, this iterated integral turns into a regular single integral, and now we're back in single variable calculus techniques of integration. What do I do with this? First of all, I see that I want to clean this up. I see that I have x squared plus a constant, so I want to use trigonometric substitution, but this should be by itself. So I'm going to write this as the integral from 0 to 1 of the square root of 4 times x squared plus 5 over 4 dx. What did you do? I multiplied by 4 over 4. And then I factored it out. The square root of 4 is 2, so this is going to equal the integral of 2 times the integral of the square root of x squared plus, now I'm immediately going to put that as a squared form. That's the square root of 5 over 2 squared dx. And now this is a square root of x squared plus a squared, which you should have trained yourself in single variable calculus techniques of integration. Now we're going to do this. Why do I need a computer algebra system? I don't. This is equal to, what are we going to do? Our substitution is going to be, x is going to be the square root of 5 over 2 tan theta. That immediately tells me that dx is going to be the square root of 5 over 2 secant squared theta d theta. And that's what they're scared of, because I know I'm going to get one more. And then that says the square root of this guy, x squared plus 5 over 2 squared, is also equal to the square root of 5 over 2 secant theta. And then, yes, when x is 0, this says 0 is equal to root 5 over 2 tan theta. And so that says tan theta is 0, and that says that theta is 0. Then when x is 1, this says that 1 is equal to the root 5 over 2 tan theta. And that says, oh my goodness, that is going to say what? Tan theta is equal to 2 over root 5. And that says that theta is going to be arctan of 2 over root 5 are my new bounds. What? How are we going to deal with that? Not with the computer algebra system, that's for sure. So that's the hot mess they didn't want to do now. I'm going to do it. This is equal to 2 times the integral from theta is going to go from 0 to arctan of 2 over root 5. Or I can deal with a clever way of using a triangle and SOHCAHTOA to save us with that horrible expression at the end in a second. This is why they give you these. What is secant of arctan of root 5 over 2? And you're like, I don't know how to do this. The key is called that theta. And then we're going to solve in a triangle, and we get to do it right here. Just a second. This is equal to, those are my horrible bounds now. This is equal to what? I got, this thing was root 5 over 2 secant theta, and dx was root 5 over 2 secant squared theta d theta. One of those cancels, and the root 5 and the root 5 give me 5. And so this is equal to the integral from 0 to arctan of 2 over root 5 times 5 over 2 secant cubed theta d theta. This one is, I should have left it as the product. This is going to be dv, because I know how to integrate that guy. And this is going to be u. I'm going to use integration by parts. Using integration by parts, this is going to give me, this is equal to secant theta tan theta plus the natural log of the absolute value of secant theta plus tan theta, evaluated from 0 to arctan of 2 over root 5. Now we get to do this. We put those, yeah, we have to put those in there. I'm sorry, but not sorry. Moving that up, I also noticed that in the formula, it's 1/2 secant theta tan theta plus the natural log of secant theta tan theta in absolute value. Evaluated from 0 to arctan. And then I had also forgot my 5 over 2. So correctly putting that up there, I get 5 over 4. This hot mess minus this one. Tan of 0 is 0. Secant of 0 is 1. So this is log of 0. So this is all gone. Now we have to clean this up and figure out what the exact value is. Leave it like that. What are we doing here? First of all, the tan of arctan of 2 over root 5 is 2 over root 5. We can cancel those. And so in these two spots, we can just put that. And then what we're going to have to do is compute secant of arctan of 2 over root 5. And you're like, well, who's that guy? Well, what I'm going to do is let theta equal arctan of 2 over root 5. And you're going to see we're going to go backwards to what is this doing? The original substitution that we used to do the trigonometric substitution. Tanning both sides, I get tan theta is 2 over root 5. Or we let x equal root 5 over 2 tan theta. But now we have a triangle. In that triangle now, here's theta. It says tan is opposite over adjacent. So I'm going to get 2 and then root 5. And then for the hypotenuse, I'm going to square. I'm going to get 4 and then 3 is where we're going to get. You should know how to do that by now. And then what am I going to use that for? Now I need secant of theta. I don't memorize those things. What's cos of theta? Cos is going to be adjacent over hypotenuse. So secant will be hypotenuse over adjacent. So it'll be 3 over root 5 is what secant is going to be. Secant theta. Secant of arctan of 2 over root 5 is 3 over root 5. What? This is equal to now. Maybe we should erase some of that. This is 0. I don't need this anymore. From this, I see that this is 5 over 4 times secant of this guy is 3 over root 5 times tan of tan, that's 2 over root 5 plus the natural log of secant of this guy is 3 over root 5 plus tan is 2 over root 5. Let's clean that up a little bit more. This is now equal to 5 times 3 times 2 over 2 times 5 plus 5 over 4, the natural log of 5 over root 5. We'll clean that up in a second also. From here, first of all, 3 over 2 plus, what is this hot mess? It says 5 over 4 plus the natural log. Rationalize the denominator. Why would I ever want to do that? Well, watch what happens this time. Getting that, I'm going to get 5, that's equal to root 5. So that's the natural log of 5 to the 1/2, which is going to be equal to, I can put the exponent on the outside. This is 3 over 2 plus 5 over 4. Exponent on the inside becomes a number on the outside. Log 5, which is equal to computer algebra system, my foot. The exact surface area of that guy is 1.5 plus 5/8 log 5. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of others on our channel. See you next time.